Okay, guys, I thought we'd have a little Alkene quiz today. I'm going to give you 10 questions now where you're going to have a go at answering the questions. I'm going to pause it in between each question so you got some thinking time in order for you to answer the question. Right, so Alkene's quiz, off we go. So, question number one. So, we've got propene here reacting with hydrogen to become propane. Which metal catalyst should we use in order to speed up this reaction? Find out on your poster which metal catalyst should be used to speed up this reaction. So if you pause that video now and give yourself some thinking time. Okay, so hopefully you've had a think and you've come up with an answer, and the answer here would be either platinum or nickel would be the two preferred metal catalysts in order to cause hydrogen to undergo an addition reaction with an alkene. Right, question number two. Right then, so this is a polymerization process, and we're making this polymer here. Okay, so this polymer here has got two carbons in the chain and one carbon coming off the chain. So what would the monomer look like? What would the structure be? And also, what would it be called in order to make this particular polymer? So you might want to pause that video now in order to give yourself some time to think about that, and then play again to see what the answer is. Okay, so hopefully you've paused, you've had a think, you know what the answer is, hopefully. Let's see if you got it right. So I always start these polymerization processes with the most basic structure, which would be two carbons linked together with a double bond. And there's going to be 4 bonds coming off here. So your very simplest polymer would have all of these as hydrogens. That would be polyethene, all of these as hydrogens. But only 3 of them are as hydrogens here, look. 1, 2, and 3. The 4th bond in our monomer is going to have a CH3 group on it. So we'd have n numbers of these to give us that particular polymer. So the structure, there it is. What's its name? Well, meth, eth, prop. So it's prop. And the double bond, if we start counting on this end, is carbon atom number 1. So it'd be prop 1 ene. And if you were interested, this polymer is polypropene. It can be used for making ropes and that sort of thing. Okay, right, so we're ready for question number 3. Right then. So, bromine reacting with ethene, giving us 1,2-dibromoethane. What I want to know here is what is the color change that you would observe for this reaction. Give yourself a little pause of the video, have a look at your poster if you need to, and think what the answer would be. Okay, so hopefully you've come up with an answer. Now this particular reaction is a very common test for an alkene, and the bromine, to start with, is orange in color. And when you add the alkene to it, the product is colorless. So the color change we're looking for here is from orange to colorless. And it's a very common test in order to test for double bond. Orange bromine becoming colorless. Right, question number 4. Are we ready? Right, so I've tried to draw the structure of ethene for you here in its orbital state. What I want to know is, what would we call this covalent bond and this covalent bond? Okay, so pause the video if you need to, give yourself a little bit of thinking time, and let's see if you can get the right answer. Okay, so you've paused, you've thought, you've found out what the answer is. Now then, let's see if you're right. So A would be referred to as a sigma covalent bond, a sigma covalent bond, where you get two orbitals, in this case sp2 orbitals, overlapping really well to give us a strong covalent bond, a sigma covalent bond. And they hardly ever break when alkenes react. On the other hand, here we've got two p orbitals. So if you imagine a p orbital is here and here, and they're trying to overlap to give us this sort of what they've sometimes referred to as banana bonds, in fact, and you can see why they are called banana bonds because of their shape. And they are referred to as pi bonds. And pi bonds are much, much weaker, well, quite a lot weaker than a sigma covalent bond. And as a result, they tend to break quite easily when alkenes react. Okay, hopefully you've got 4 out of 4 so far. Here's question number 5. Right, what is the name of the mechanism for the following chemical reaction? Okay, so we've got ethene reacting with HBr, hydrogen bromide, to give us 1-bromoethane. What is the name of the mechanism for that particular chemical reaction? Okay, give yourself a pause, have a look at your poster if you need to. Let's see if you can get the right answer. Okay, right. Now, this is an easy question in many ways because alkenes really essentially only undergo one type of chemical mechanism. And there's a big clue to the fact that we've only got one product here, so this HBr has added itself across that double bond. So it's an addition to start with. It's an addition. And in most cases, alkenes undergo what we call electrophilic addition. Electrophilic addition. That would be the mechanism for the reaction of most alkenes. Right, question number 6. Okay, now I'll try to draw out a mechanism for you here, a mechanism of electrophilic addition, in fact. But there are 2 errors in this mechanism. Now you might need to give yourself quite a lot of pausing time here, so pause the video and have a think about if you can spot out these 2 mechanisms. Give it a pause now, and we'll come back with the answer. Okay, you spot them, see what they are. Right, so first error is here. This pair of electrons is not going to be attracted towards a partially negative charge. We needed to flip this bromine over the other way in a sense. So the charges need to be delta plus and delta minus. It's the delta plus on here that's attracting these 2 pi electrons over onto the bromine. So that's our first error. And our second error, we spotted it. It's in this bromide ion. This negative charge represents a pair of electrons. The arrow shows just 1 electron. That would be like a radical mechanism. We needed to show a double-headed arrow here, indicating a pair of electrons. So there was your second error. First error on the charges, they were wrong way around for this particular mechanism, and the second error with that single-headed arrow rather than a double-headed arrow. Okay, ready for question number 7. Which of the carbocations shown here is most stable? A, B, or C? Now, carbocation is a carbon with a positive charge. And that carbon is not going to like that positive charge because it's electron deficient. It's only got 6 electrons surrounding it in each case. However, some carbocations are more stable than others. Can you decide whether it's this, A, B, or C is the most stable of these 3? Pause it now, give yourself some thinking time, and we'll come back with the answer in a second. Okay, right, did you get it? Let's think about this. Now, carbocations are stabilized by electrons being pushed towards them. They are electron deficient. They really need more electron density. And what pushes electron densities towards atoms are alkyl groups. So, in this case, this A has got 2 alkyl groups pushing electron density onto that carbon. That's not bad. This B has only got one alkyl group pushing electron density onto that carbon. It's not particularly stable at all. But this one over here has got 3 methyl groups pushing their electron density onto that carbon. And therefore, it's C that's going to be the most stable. That is a tertiary carbocation. Tertiary carbocation is going to be more stable than a primary carbocation and also more stable than a secondary carbocation. So the order would be the most stable, the second most stable, and the least stable. Hopefully you got that right. Okay. Question number 8. Can you name the product formed in this reaction? Okay, can you name the products formed in this reaction? So you need to probably draw out the structure first, and then you're going to have to name it. So give it a video a pause, have a think, and see if you can draw out the structure and then give me its name. Okay, right, see what you got. So this bromine is going to add across this double bond, an electrophilic addition again, like all alkenes do. So let's draw out the structure of that product. So the CH3 at the end here is not going to be doing much at all. That CH will now have a bromine attached to it. That CH will also have a bromine attached to it. And this CH3 over here will have nothing new attached to it. So here's our product, electrophilic addition of bromine onto methethprobutene. It's going to give us, can we name it? It's going to be 1, sorry, no, my mistake, 2,3 dibromobutane. So that was the answer to question 8. 2,3 dibromobutane. Okay. Question number 9. What is the name of the dominant product in this reaction? The dominant product. So, if you remember in your poster, we talked about non-symmetrical alkenes, like this butanene, can form more than one product when HBr adds to them. I want to know what the dominant product is here. Right, give the video a pause, have a think, see if you can come up with the right answer. Okay, so the 2 products that could be formed here depends on which way around the bromine and the hydrogen attached to this particular alkene. So 2 possible products, one of them I'm going to draw up here, H2. So I'm going to attach the hydrogen onto this one here. So CH2, CH2Br, that's one possible product. And then the other possible product would have the bromine and the hydrogen flipping themselves over, if you like, and attaching the other way. So instead of the hydrogen going on this one now, I'm going to draw the bromine on there. And I'm going to put, instead of the bromine on this one, I'm going to put the hydrogen on there. Okay, so which of those is the dominant product? Did we get it right? 99% of this one, and about 1% of this one. So the dominant product is the one that results from the secondary carbocation. This would have had the secondary carbocation in the mechanism. This would have had the primary carbocation, not as stable. This is the one that's going to produce the most of. What is it called? Could you name it? Well, it's clearly 2-bromo-methethprobute 2-bromobutane. That was the answer to question number 9. Okay, last one then. Last question. Question number 10. What colour change would be observed in this reaction? What colour change would we see? What colour would we see at the start? What colour would we see at the end? Okay, give yourself a pause. Pause the video for a second. Have a think about, see if you can come up with the answer. Okay, so I've been a bit mean here because I've given you a product that you've never seen before. The only thing you needed to know here is that this stuff is used to test for alkenes. And this stuff is potassium permanganate, KMnO4, and this is a dark purple colour. Dark purple colour before it reacts. As soon as it comes into contact with an alkene, it'll become colorless because this product here is colorless. You didn't need to know what that product was. You just needed to know that potassium permanganate goes from dark purple to colorless when it reacts with alkenes. There we go, 10 questions on alkenes. Did you get 10 out of 10? If you didn't, why not? What do you need to go over to make sure you can get 10 out of 10?